Hello folks, here are some energy work and conservation of energy questions. This question is telling us we just let go of a car from the top of a hill. It rolls down, reaches to another point 5 meters below the initial point. Write down the conservation of energy and think about what type of energy conservation happens here. The question doesn't say there is no friction, so there will be some energy lost to friction along the way, which will be how much energy converts to thermal energy. Energy cannot be actually lost. It converts from one form to another. So that will be happening initially. At point A, the car will have only potential energy, no kinetic. We just let it go from there. And at point B, it will have kinetic and potential energy. We start with our general conservation of energy equation. Initial plus if there's any work done on the system minus thermal equals to final. There's no work done on the system here. No external forces are pushing or pulling on the system other than friction. Friction converts some energy to thermal energy. We take that away and equate it to final energy. Initial energy is energy at A. Take away the thermal energy equals energy at B. At A we only have potential energy. We put that down. Kinetic is 0. And minus delta E thermal will be at B. We have both. We have velocity, we have kinetic energy, and we have potential energy because we have height. Here's an example involving that. We have a car with mass 3,000 kilogram. Friction 6,000 Newton in between car's tires and the road. Car skids to a stop in 5 meters. What is the initial velocity? That's what the question is asking us here. We'll start with initial energy minus any thermal conversion plus the work done is equal to final energy here. There is a thermal energy conversion. If there's a friction, there will always be a thermal energy conversion. And that will be equal to work done by the friction. So I'm going to call it here work of friction is always equal to change in thermal energy. That's how much energy goes into the heat. And work, as we know it, is always equal to force times the distance. And here it will be force of kinetic friction times the distance d. Notice here force and distance are anti-parallel, so angle cosine 0 cosine pi will be 1, so no angle d, no cosine needed here. We have cosine pi, which is minus 1, which is why the C thermal that comes here as minus, but let's not worry about too much algebra here. Force and the anti-parallel, so we just multiply force and the distance to find the work done. Put it here as a thermal energy. Now at initial point, I'm going to call this point A. We have kinetic energy, so we have Ka bigger than 0, but potential energy is 0 at A because no height. At B, the car stopped, so kinetic energy is 0. No height, so potential energy is also 0. So now the energy at B. We're going to turn this into energy at A minus delta E thermal is equal to energy at B. Since there is no other forces pushing or pulling on the car, work done on the car is 0. There's only work done by the friction, which is the energy that converts to thermal energy. At A we have kinetic A, 0 potential, minus delta E thermal equals to 0 because at B we have no energy. That gives us that kinetic energy at A should be equal to how much energy converts to thermal energy. We can also logically think here, since the car stopped, initially it only had kinetic energy, and all that energy is eaten by friction converted to thermal energy, so they should be equal, which is what we found here. So this is more technical approach going down here. More practical approach would be just logically thinking all this kinetic energy should have been turned to thermal energy by the friction, and that's it. and you're gonna get to the same result. So 1 over 2 mva squared, then it should be equal to kinetic friction force times the distance, because we decided that's the thermal energy. And here the velocity at A would be equal to initial velocity, and done. To solve for VA here, which is V initial, which is what we're looking for, I would multiply both sides by 2, divide both sides by m and 2 will cancel here, right? I'm gonna have this on the right hand side. Left hand side, let me carry this to here a little bit, will be VA squared, and that's equal to 2 of kinetic d divided by mass, taking the square root of both sides. We will have VA is equal to square root of these values. 2 times F kinetic times distance divided by mass, and that is equal to, putting in the values, 2 times 6,000 Newton times 5 meters divided by the mass of the car, which is 3,000 kilogram, and that should give us a velocity of 4.47 meters per second. This question I'll leave up to you to solve, similar to what we had in the initial one. A child is going down a slide here, make an ugly picture and work on it, think about it, ask me questions if you get lost. I'll skip that. This question is a simple question, other than that, except for the fact that we have to deduce some information from this graph. So it tells us your Achilles tendon stretches when you run, behaves like a spring, stores some energy that is returned to you when you push off the ground with your foot. In the figure right, you see data for force versus extension for Achilles tendon and attached muscle for female subject. When she runs, the maximum stretch is 0.5 centimeters. What energy is stored? The stored energy would be spring potential energy. So I'm going to go check my notes and write down the equation for spring potential energy. That's 1 over 2k x squared. X is given to me here. That's the stretch in the spring, the tendon as the spring here. 0.5 centimeters. That's equal to 0.005 meters divided by 100. Okay, I'm gonna rewrite that. 0.005 meters. Insert that in here. Insert k. I can solve this. Kind of a plug-in-chug question, but we don't know k. That's what makes this questions a bit more interesting. We find k using this graph. If we are stretching a spring, let's remember that from its initial position, we pull it down a little bit. We have to apply a force to do that, an amount of x, and the spring will be pulling back on us, and that's equal to kx. Remember, don't worry about the negative sign here. I've told you, as you hopefully remember, because we just look at the magnitude of that force. And from here we can say if F is equal to kx, we can solve for k, F over x. And you can take any point from this graph to solve that. That would be actually slope of alpha, which is tangent alpha. So it will be rise over run. I'll just put here tangent alpha from the graph. It's essentially any force you can take, find the corresponding stretch, will give you the same answer here, but we're going to take the end point here. So K is equal to, at the end point here we have 400 Newton, and that's divided by the distance of string, 0.24 centimeter. Convert that to meter, it will be 0.0024 meters. That will give me 1.6 times 10 to 4 Newton per meter. And insert that in here. I'll solve for my U spring. Should be, it's actually 1.67. I'm gonna put more information there. Times 10 to 6. That's an error there. Let me check my numbers here too. Yes, times 10 to 6, not 4. To 6 newtons per meter times 0.005 meters squared. That will give me a spring potential energy of 2.08 joules. Okay. Next question has the solution already, very similar. I'm gonna test this quickly. We compress a spring, put a ball. This is simply a toy gun. Let it go, and the question is asking us what is the final velocity of the ball we put in this toy gun. Initial is 0, so we can start writing down all the equation. You know, thinking about thermal. Ignoring friction here, the question tells us ignore friction. We'll end up finding this. Initially stored spring potential energy converts into kinetic energy. So you can, if you guys feel like and understand the question, no friction, that's important here. No other sort of potential energy, no gravitational potential energy. So initial spring potential energy converts into final kinetic energy. You can jump ahead here and solve for the final velocity. If you go by, techniques, initial plus work minus E thermal equals final energy, you'll say no work done, no thermal, friction is ignored, initial is equal to final. Initial is only spring potential, no initial kinetic energy. Final is only kinetic energy, no spring potential. Put in the values and solve for the velocity. 1 over 2kx squared will be equal to 1 over 2 mv final squared. Alright, let's look at this question here. Queen is at rest at the top of a playground slide. The main part of the slide is 5 meters long and it is tipped at a 30-degree angle. Queen starts sliding, moving down the tipped section, and then the slide levels out so that he leaves the slide at 2 meters per second. So I know final velocity. I know initial velocity is 0. I'm going to call these points A and B. I can leave them as K, initial and final as well. Alright, if Queen's mass is 24 kilogram, let's put this down. How much thermal energy is deposited in his trousers and in the slide? So we are asked to find thermal energy here. Apparently there is friction, some energy converts to thermal energy in between here. We're going to start with our energy initial plus any work done minus thermal energy equals energy final. no work done, we end up having energy initial minus E thermal is equal to energy final, and solve for E thermal. We'll have E thermal is equal to initial energy minus final energy. We call this initial point point A. At the initial point we have a potential energy UA and no kinetic energy because there's no velocity, so KA is 0, not B. At point B we have kinetic energy, but potential energy is 0. And that's it. So we'll say E thermal then is equal to potential energy at A minus kinetic energy at B, right? Initial is only potential energy at A, and final is only kinetic energy at B. And that is it. We're almost done. We'll put at UAMGH minus kinetic energy. Oh, that's B. That's B. Sorry about that. At B, 1 over 2m V final squared, final velocity there, and solve for E thermal. Now one thing here is that we don't know h, but it's really easy to find h. If we know this distance and the angle, we can go with this. Sine 30 is equal to opposite divided by the hypotenuse. So h here, height will be 5 times sine 30. If you do this, you'll find your height to be, let's see here, 2.5 meters. Insert that in here. We know mass, insert everything. So for E thermal, you'll find that to be 540 joules. Make sure you insert everything and solve and understand the logic here. This one, simple, a similar question. What I want to do on this one is to take my zero potential to be, let me delete that and draw maybe a straight line. I want to take my potential, zero potential point to be this, because I can pick any potential. Any point is zero potential. So I assume this is my zero potential point. And then I'm gonna ignore this part over here. This is something we can always do to ease our work. What I have to be careful about is that then I have to take this distance here as my height, which is 20 meters. So the question tells me find the velocity of the roller coaster in the figure below at the finish point. I'm going to call this actually V final. Assume that the total mass of the roller coaster is 200 kilogram. So we know the mass. And it's also given the initial velocity V0 or V initial. I'm going to call it VA. 0 meters per second. I'm going to call this point A, this point B. At this point, the roller coaster will have a velocity we don't know. I'm going to call this VB or V final is also fine. One thing I want to say here, ignore friction. We don't want to have friction here. I'm missing part of this question. Initial energy minus any thermal that comes from work of friction plus any work that an external force could do on the system is equal to E final. This is 0 here, friction is ignored 0, so initial energy is equal to final energy. What is initial energy? At A we have 0 velocity, so kinetic energy at A is 0. There's a potential energy. At B we have 0 height, so potential, this is VB by the way. UB is 0. There's a kinetic energy. Let's write them down. Potential at A plus kinetic at A, no other sort of possible energies, is equal to potential at B plus kinetic at B. Potential at B is 0 and kinetic at A is 0. So we end up having mg HA is equal to 1/2 mvb squared. This is what we're looking for. We don't even need the mass. They cancel. Height with respect to the 0 point I choose for A is this 20 meters. Insert those in and solve for velocity at B. If I work this out with the similar algebra as the previous question I showed you, we'll have VB is equal to square root of 2 GHA, and that's it. Insert in all the values. Again, HA is 20 meters, G is G. You'll find the VB value to be 19.79 meters per second. That's the final velocity the question is talking about. Alright, hope this was useful. The rest we discussed already, all similar ideas. This is another way of writing the energy conservation. This is equivalent to the way I like writing it. K final plus U final. No, I'll write this in my way. Let me erase this. Energy initial, which would be this guy over here, right? Plus work minus energy thermal. This is to give you guys an idea that that's the energy loss to friction. We always like remembering this as a loss to friction. It's actually converts to thermal energy, and that's equal to E final, which would be these values here. We can apply these to projectile to solve for any question related to velocities. We don't have to go through all those equations. For example, if you throw a ball vertically up with an initial velocity of 22.6 meters per second, let's say this is this ball over here, it had an initial velocity 22.6 meters per second. What is the highest point it can reach? So we know if it reaches to the highest point, its final velocity will be 0. I'm taking this to be my 0 U point, ignoring this height. If the question wants me not to ignore it, it will give me its value, but we ignore it in this part, assuming we throw it from the ground. And the highest point it can reach, I can call it H maximum, can be found using energy conservation. I'm going to call this point A again, this point B, and let me choose another color here so we'll be separate. Energy at A. Okay, undo that. Energy at A plus any work done minus any thermal energy equals energy at B. We are ignoring air friction generally, although it's not mentioned. So thermal energy conversion will be 0. No work, no outside forces throughout the motion on the ball. So work is 0. Energy at A is equal to energy at B. At A, I only have kinetic energy. No height, no potential energy. And at B, I have potential energy. No velocity, no kinetic energy, so that will be 0. And then I'll solve for the height. Potential energy at B is equal to kinetic energy at A, so I'll say 1/2 mass times VA squared, that will be V initial, is equal to mgHb, that would be H maximum. Because the maximum height, the ball will have 0 velocity. And that's V initial. And you're going to solve for that V initial. and it will be equal to square root of 2 GH maximum. You don't even need to know the mass. Keep that in mind. Let me see if I have a number for that. So H maximum will be 26.06 meters. I'm gonna check that out quickly. So we'll do square root of 2 times 9.8. Oh, sorry, there's an error here. We're looking for H maximum, not V initial. Oh, let's delete that, folks. The result is correct, only I made a mistake by put an equation for initial velocity. We know initial velocity. We're looking for HB, H maximum. So from here, H maximum will be masses cancels, will be VA squared, or V initial squared divided by 2 G, and that should give me 26.06 meters, and that is the value I'm gonna check. Alright, that's correct. This one is a similar question, except we have a slightly different version of the equation here. I'm gonna leave this up to you folks to decide what the H maximum should be. Again, ignore the height from the ground you see here. We're assuming we kick the ball from the ground. Our U0 point is here. The H maximum the ball will reach will be right there at H maximum. This guy will have a velocity though, and it will be only X component. That's the difference here. X component is equal to V initial cosine the angle, which is 30 degrees here, the initial velocity mixed with the horizontal. So this will be V initial, this is 30 degrees. So the question is telling me the guy kicks the ball from the ground with this V initial 30 degrees from the horizontal. What is the maximum point it can reach? And what is the velocity of the ball at 0.7 meters from the ground? A and B. So let's say this is the 0.7 meters ground. Call the initial point A, this point B, maybe this point C. So part A, you'll say energy at A plus work minus E thermal equals energy at B, but you know, air friction is ignorable, no work is done, so energy at A is equal to energy at B. At B you have kinetic and potential, so UB is there, KB is there. That will help you find the velocity at B. There will be a velocity B. Let's call the initial velocity velocity A. You'll put those down. So at A we have kinetic energy, but potential energy at A is 0. So you can put down all these. Kinetic energy at A plus potential energy at A is equal to kinetic at B plus potential at B. We know potential energy is 0 at A. Put in the values. 1/2 mVA squared equals to 1/2 mVB squared plus mGHB. You're looking for this guy, you know all the rest. 0.7 meters would be your HB. That's part A. Solve this. you will have a velocity. I should have somewhere here. Should have a velocity of 14.54 for B. Check that out. Meters per second. At B, for B, you're at the highest part here. Apply the same. You'll have energy at A is equal to energy at C. You'll have kinetic energy at A, no potential, and that will be equal to kinetic energy at C plus potential energy at C. And to solve for H maximum from there, which will come from potential at C. So your kinetic energy is still 1/2 mVA squared at A. At C, 1/2 mVc squared is your kinetic energy. Potential energy is mg hc, which is H maximum, right? The maximum point is the C, as we call it. So hc is equal to H maximum, and Vc is equal to the x component of initial velocity. Remember, for this projectile, horizontal component always constant, and it's equal to Vx initial. This C here is an under subscript. Don't think it's a different value, folks. So subscript. This is Vx initial. Find those, insert them in, and as I put here, Vx or Vx initial, which is never changing, right, is equal to V initial cosine 30 in this case. And so for H maximum, and the value you find should be 2.87 meters. Alright, hope you all like these.